Shall we start the program?
Yes, Surya.
Yes, sir, Neeraja miss.
Surya, am I audible?
Yes, ma'am. Yes, ma'am.
Okay. You can start the program. Sir?
Yeah, we will start the program. Yes.
Okay, sir.
Okay, sir. So participants, we are starting the program. Good afternoon to each one of you present here. I'm Surya M. Nair, Assistant Professor, Department of Civil Engineering, JECC Thrissur. I'm your host for the day. The one good thing about pandemic is that it has helped us to explore the virtual platforms, and today, because of that, we have here people from different parts of the nation gathered together to gain some knowledge. We are truly delighted to have you all here with us this afternoon. The workshop is curated by Department of Civil Engineering, Jyoti Engineering College, in association with IST Students Chapter. The design of concrete mix is not a simple task of mixing the ingredients. There is more to it. Concrete mix designs is an aid to foundation to achieve sound infrastructure. The aim of the program is to bridge the gap between the theory and practice when it comes to concrete mix design process. A gentle reminder before we start. If the participants have any queries during the workshop, kindly post it in the chat box. Please keep yourself in mute mode when the class is going on, and participants will have the opportunity to ask questions at the end of the workshop in the question and answer session arranged. Feedback links will be provided at the end of the session in the chat box. Begin with gratitude. Gratitude unlocks the fullness of life. It turns what we have into enough and more. Let's begin the session by seeking blessings from the Almighty through a minute's silent prayer. Thank you all. Without any further delay, I invite Ms. Neeraja PG, Assistant Professor, Jyoti Engineering College, for the welcome address. She is also entrusted with the task of introducing our renowned speaker, Dr. Jagdish Vengla sir, to the participants. Neeraja Miss, over to you.
Thank you, Surya. Good afternoon, all. It gives me immense pleasure to extend a very warm welcome to all of you present here on behalf of Civil Engineering Department, Jyoti Engineering College. First of all, it's a great honor for me to introduce and welcome our chief guest, Dr. Jagdish Vengala, Head, EEDC Incubation and Innovation Center, Associate Professor, Department of Civil Engineering, PVP Siddhartha Institute of Technology, Vijayawada. He was former HOD in Department of Civil Engineering, BMSIT and M Bangalore, and scientist in IPIRTI Bangalore, and also design engineer in Torsteel Research Foundation in India, Bangalore. He is having publications of more than 40 in national as well as international journals and have guided for more than 30 research works. He had reviewed and chaired more than 50 programs. He is also having 3 ongoing PhD guideships. We are immensely blessed to have such an eminent personality to chair today's workshop. Sir, warm welcome for today's workshop. Next, I would like to welcome our Head of Department, Dr. Jacob Chandapillai sir, to this function, and my all colleagues. Last but not least, I welcome all our beloved participants. Welcome all for the function. Now I welcome Sir, Chief Guest, to this function. Sir, over to you, sir.
Yeah, good afternoon. So thank you, Neeraja, for inviting me to deliver a talk on concrete mix design. It gives me pleasure to deliver my favorite topic, concrete mix design, on behalf of Jyoti Engineering College, Kerala. So let me share my presentation. Hope you can see my presentation.
Yes, sir.
Okay.
Visible.
Yeah, thank you. So when you talk about concrete mix design or mixer proportioning, it is both art and science. Why I'm saying? Because you are mixing different constituents, and the properties of these materials, whatever you are mixing, whether you take cement or coarse aggregate or fine aggregate or water or any other admixture, whether it is a chemical or mineral, each material having a different property. So to mix them and make them in one strongest construction material, so it requires, you need to know a little bit of science, and you need it's also a kind of art. So before getting into the topic, why mix design is required for normal concrete? Because many a times we might have seen in our places, particularly the small residential buildings. I want you to see this particular video. So typically the mixer operator, he actually decides how many, the quantity, how much quantity of coarse aggregate, fine aggregate, and the water has to be mixed. And once it got mixed, he decides, without proper mixing, sometimes he may put that concrete mix for dumping into the site. You can see, I just wanted to carefully see now. The mixer is getting rotated, and she has put the coarse aggregate, and immediately after she put the coarse aggregate, without properly getting mixed, is placing the concrete, the same concrete is being dumped on one of these slab portion of a particular house. So what I mean to say is here, so many of the sites, concrete is getting abused without having a proper mix design. And also many times they are based on the volume batching. So quality control of the concrete is definitely a question mark all the time. You cannot definitely leave it to the judgment or guesswork of the concrete mixer operator or a contractor. So from the video, you can clearly see how the concrete is getting abused without having a proper mix design, and it is getting placed, and they are placing it in one of the elements of the house. So it is a little bit complicated because any of the variable changes, whether it is a coarse aggregate or a fine aggregate or cement or water, the entire properties of the concrete may oppositely affect. It will change. It will affect the concrete mix design. The aim of the concrete mix design or mixer proportioning, you need to understand four very important parameters. One is the workability. When the concrete is in fresh state, you can able to place it properly, transport it properly, And at the end of the curing period, it has to achieve the strength. And also the concrete what you placed, it should be durable in nature after 3 years, 4 years, 10 years, 20 years. So the concrete, whatever you are placing, it should be durable in nature. And also at the same time, the mix, whatever you are preparing, it should be economical in nature. So based on these 4 very important requirements, you prepare the concrete mix. But when we look into the traditional concrete mix design method, that means the volumetric batching, what we see earlier, they used to say like 1 to 4, 1, 3, 4. So 1 is cement and 2 is sand and 4 is a gravel proportions. Typically, what we mix these materials in volume by volume. And water content, we add it to whatever the workability requirement is. So this is more of a volume batching, and the quality of the concrete is a question mark. But when you are designing the mix based on the mass of the components, it is more reliable in nature. I just wanted to give you an example here based on the weight versus volume batching observations. When you look into the mixed proportions, suppose you take 1, 1.5, 3 or 1 to 4 or 1, 3, 6, the weight equivalents, if you take it or if you calculate, you can see the coarse to fine aggregate ratio in case of 1, 1.5, 3 is 2 in case of volume and 1.663 in case of the weight equivalent. So when you compare these 1, 1.5, 3, 1 to 4, 1, 3, 6 mixes, both in terms of weight and both in terms of volume, and compare the strength, you can see the way batched mixes, you got the more strength when compared with the volume batching. This is one of the study conducted by Joshua et al. So what I mean to say, you have to go for the way batching rather than the volume batching. Very, very important point. And some of the principal factors, as I've discussed earlier, the first is workability. After preparation of the concrete, it has to be transported properly without affecting the properties, and it has to be placed in position, either pumping or by placing, dumping. And also, it has to ease with the compaction when you are using the compacting equipment. So we generally measure the workability in terms of slump. And next is the strength of the concrete, what we call characteristic strength of the concrete. And also, one of the factors that affects the mix design is the type of cement you're using and its strength at 28 days. Many times at sites, they'll be having about 53 grade and sometimes Portland Pozzolana cement, PPC, and Portland slag cements. So you have to be very careful about what type of cement you are using and its strength. So you have to test the basic properties of the cement, what you are using at the site. And 2 more important considerations one has to look into is the minimum cement content and the maximum water cement ratio. So when we talk about the durability considerations or exposure conditions, these 2 parameters are very, very important. So the mix design, the grade of the concrete also, we decide based on the exposure condition. Many people, they think, we do reverse in the sense, suppose if you take the M30 grade of concrete, so we actually, M30, the cement is this much, the maximum water cement ratio is that much for columns or beams. We think in that direction. But generally, you have to consider the exposure condition of the element. So based on the exposure condition, we design the concrete mix, whether it is M20 or M30, M40, we decide based on the exposure condition. Very, very important point here. And aggregate properties affects a lot. Is it a graded aggregate? Is it a rounded aggregate? The shape and the size, is it like 20 mm down or 12 mm down or 10 mm down? Or the surface texture, is it rough? Is it smooth? So these are the factors which will affect the concrete mixer proportions. And all the proportions, all the ingredients you measure by weight per unit volume of concrete. So what is the basic objective of concrete mix design? Some of the objectives are, it has to meet the strength. The first and foremost is strength requirement it has to meet. Second is the durability requirements, because I'll just give you an example here itself. Suppose you have a normal weather condition that is mild. You're going to build a small structure. So for columns and beams, mild exposure, the minimum grade of concrete you have to go for is M20 grade. But when you are going for the footings, that is the foundation footings, so the concrete which is buried under the soil, the exposure condition comes as moderate. So the minimum grade of concrete for a normal weather condition, wherein you are using M20 grade for both beams and columns, but at the same time, same structure, because the footings are buried under the soil below the ground level, you are going for moderate exposure. The moderate exposure, the minimum grade of concrete is M25. That is why we are talking about the durability requirement. So durability requirement is based on the exposure condition, the environment surrounding to the structure, based on the the surroundings or the exposure condition, we design the grade of concrete. And when you are the next point, when you are designing the mix, you have to see that can you able to mix it? If it is a complex structure, is it possible to compact it? So if you are unable to compact it due to the complexity of structures or congested reinforcement is present, you will just pour the concrete. That's what we talk about, the self-compacting concrete. Suppose if you have to pump the concrete to a 11th floor or 12th floor, you use the pumping mechanism using concrete pumps. So you have to make the concrete such that it can able to pump from the ground floor to the 11th or 12th floor. Next is at the end of the placing, it has to give a satisfactory appearance. The view should be proper, and also it is as economical as possible. These are the objectives of concrete mix design when you are going for the mix design. So what is the process of the concrete mix design? So what we do, based on the past experience or any of the published data, or the information obtained from the properties of the materials, we design the initial mix. And based on the initial mix, whatever you have designed, then you do the trial mix in the laboratory and then you test it. I have worked in Torch Steel Resist Foundation India way back in 2002 to 2004, wherein while working there, I have designed more than 2,000 concrete mixes during that time. 2,000 trials we have done. And once you do the trial mixes in the laboratory, you test it, and then before starting the project, whatever we give, small modifications can be done at the site. That's why they do full-scale trials before construction begins at the site. So any of the changes, small changes due to the material change, they will tune it to the site requirements. So this is how the process of concrete mix design happens, from the theory to the practice. These are the three stages. This is the very important table in IS 456. One has to properly understand this table. So I'm limiting my talk to reinforced cement concrete. Most of the structures we go for the reinforced cement concrete RCC structures. When you look into the right-hand side table, as I mentioned very clearly, we design the mix based on the exposure condition, the first and foremost point. Suppose you are in a coastal region, whether it is a Mangalore or it is a Machilipatnam or any other, or Mumbai, the coastal exposure condition, either it is a severe or it comes as a very severe. It depends on the element also. So for coastal, the exposure condition is say severe, then you are going for the reinforced concrete structure. For severe exposure condition, the minimum grade of concrete you have to go for is M30. When you're going for the M30 grade of concrete, the minimum cement content you have to use is 340 kg per cubic meter. And the maximum water cement ratio you have to limit at 0.45 for the severe exposure condition. So similarly, as I mentioned the example earlier, for a normal weather condition, the structure, the columns and beams, if it is a mild exposure, then you're designing the M20 grade of concrete. When you are designing concrete, because it is buried under soil, you have to go for the M25 grade of concrete because it comes under moderate exposure. So mild to moderate, the difference is the minimum cement content you have to maintain as 300 kg per cubic meter, but you have to limit the water cement ratio to a maximum of 0.55 in case of mild and 0.5 in case of moderate. So what I mean to say here is exposure condition is very important. Based on exposure condition, you decide the minimum grade of concrete, and accordingly you will choose the maximum water cement ratio and minimum cement content. So the maximum cement content we can go for, as per IS 456, is 450 kg per cubic meter. IS allows you to use mineral admixtures in the replacement of cement as long as you get the required grade of concrete, whether it is a fly ash or GGBS or any other mineral admixture. And also you can reduce the water cement ratio and get the required strength. At the same time, you can get the slump by adding chemical admixtures. So when you look into the table, for the normal concrete, you can see the cement varies between 300 to 450 kg per cubic meter. And the maximum water cement ratio, we start with 0.55 in case of RCC. And the grade of concrete is M20 to M40. Now one can go for M60, M80 nowadays. People are using it at various sites. And IS permits you to use various mineral and chemical admixtures. The most commonly used mineral admixtures nowadays at site are fly ash and GGBS. And some important cases, to get the early strength, people are using silica fume or any other materials, other mineral admixtures. So here, you need to understand what is the role of the chemical admixture. When you take the normal, a particular mix having 0.55 as a water cement ratio and slump as 75 mm, strength is 51 MPa. Suppose if you wanted to increase the slump by adding plasticizer, you can increase the slump without affecting the strength by adding plasticizer. Another advantage of adding plasticizer is without increasing the slump, by maintaining the slump, by reducing the water cement ratio, you can increase the strength of the concrete. from 51 to 63 MPa. So in one of the case, wherein we maintained the 75 mm slump, but water cement ratio we have reduced from 0.55 to 0.44. So using plasticizer or chemical admixture, particularly plasticizer, water reducing admixture, you can either increase the slump or increase the strength. So you can see, based on the flow table spread to amount of water in concrete, to make very high strength concrete, the amount of concrete we go for is like 160 to 140 and so on. This is without, up to 160 without superplasticizer. With superplasticizer, you can come down up to 140, 135. If you want to make flowing concrete, one can go up to, without superplasticizer, you can go up to 240. And with superplasticizer, you can reduce it to 200, 220. As I mentioned, IS 456-2000 clause 5.2 allows you to use the supplementary cementitious material or mineral admixtures as a part replacement of cement in the concrete. Some of our fly ash, metacavalin, microsilica, rhesus cash, alcofines, fine form of GGBS, and microsilica. So any of the mineral admixtures you can use. Why do we have to use the mineral admixtures? What are the advantages? Before getting into the example of the concrete mix design, I just would like to give you a small overview. What is the basic reaction when you add the water to the concrete or when you add water to the cement or the mixture? So water, which is OPC, ordinary Portland cement, is the binding material, reacts with water and hydration process starts. The final end product is calcium silicate hydrate, CSH gel, along with a calcium hydroxide or excess lime that is formed in the concrete. When you add any of these supplementary cementitious material or mineral admixture, whether it is a fly ash, silica fume, or GGBS, the excess lime that is present in the concrete, that is calcium hydroxide, will get again reacted with this supplementary cementitious material. That's what we call it as a secondary reaction that happens and again forms more CSH gels. So the excess lime that is present in the normal concrete, when you add the mineral admixture, it produces more CSH gels, so the more strong concrete, you can see. So what are the properties of concrete with these pozzolaners? It will increase the strength. It will increase the impermeability. Why? Because you have more of CSH gels that will form in the concrete. So it will reduce the voids. So it will increase the strength. At the same time, it will increase the impermeability. So it is not permeable because more of the voids gets filled with these CSH gels. And also the compressive and tensile strength will increase because of the lack of bead pockets or less voids, wherein dense hydrated cement paste, the more CSH gels gets formed within the concrete. That is why your compressive and tensile strength will also increase. Coming to the properties of the aggregates, many times, for bigger projects, the project in charge or the project manager goes to the site and selects crushers and select the aggregates, which type of aggregate they want. They avoid flaky or elongated coarse aggregates or aggregates. So, based on our observation, it is very evident that when you compare the jaw crusher aggregates to VSI, vertical shaft impact crushers, you will get a uniform aggregates when compared to the jaw crusher aggregates. So you have to make sure that it is either square or angular in nature. You have to avoid the flaky or elongated aggregates in your concrete mix. it is very important to combine different aggregates to make sure you get a graded aggregate. So the basic mix design is to have the less voids in the concrete. If you have a different sizes of the aggregates within the concrete at a different size fractions, less voids will get formed. So that is why always when you're going for coarse aggregates, as per IS 383, it is very important not to go for single sized aggregate. If you find 20 mm down is a single sized aggregate, you mix 10 mm down aggregates to make it graded and make sure you use a graded aggregate in your concrete mix. So these are the limits given by the IS 383. One has to make sure you got a graded aggregate or not before using it in concrete. Coming to the condition of the aggregates, the moisture. Moisture is very, very important parameter. If continuous rains are there, if the aggregates got wet and completely submerged in water for quite a number of days or 2 to 3 days, it is completely saturated and surface is wet. So we call it as a saturated surface wet. Suppose if you make the outer surface dry, but aggregates are saturated, so we call it as a saturated surface dry. For mixed design purposes, it is very important to note that we consider Ssd condition. Many times people say Ssd condition. What is Ssd condition? We always consider the aggregates are in saturated surface dry condition. That is why we actually, make the corrections for both the moisture correction and also the water absorption corrections because of the very basic basic nature of Ssd condition. We take it for calculating the concrete mix. Air dry is outside dry, and only the surface periphery gets dry. The inside, not inside. Inside you have a little. Oven dry is it's called bone dry. Okay, so we do not include water needed for absorption. Okay, so these are the four types of the conditions we consider for the aggregate moisture. But when you are designing the concrete mix, we take Ssd condition while calculating the concrete mixes. This is what I am talking about, the lowest void content principle. You have the gravel with you and you have the sand with you. There is a very interesting test one can do to determine the least void content. What is the aggregate skeleton you get with the least void content? You take a 5-liter container as per ISTM C29, which you usually determine the dry density of aggregate. We actually determine loose density of aggregates and rodded density of aggregates. So you have to take different mixes because 60-40 is the most common, like 60 is your coarse aggregate and 40 is your sand. And depending upon the zone size, you change that 60-40 or 60 to 38. So different sand to gravel ratios you can take, and you can find the density of the various proportions or ratios, and you can find the lowest void content practically using this particular method, and you can adopt that method in your concrete mix design. Suppose if you are using the new material, or if you don't have much of the data, or if you are interested, you can go for this lowest void content. So here you have to find the packing density. Packing density is nothing but solid volume to total volume, wherein you see that you get a better packing density. That means the least voids in the mix. So let me explain the concrete mix design as per IS 10262. Earlier it was 2009, and now it is 2019 new concrete mix guidelines. Both are same. I will explain you how exactly you design the mix. So some of the highlights of IS 10262 2019 are, it is divided into 3 different grades. One is the ordinary, it is like M10 to M20. Standard grades are M25 to 55. And high strength is between M60 to M100. These 3 types of grades of concretes you can design using IS 10262 2019. So some of the other highlights are, they have given the general guidelines, and ordinary and standard grade separately they have given, and high strength concrete they have given, and also 2 more special concretes they have given. One is self-compacting concrete, and another one is the mass concrete. So these are the information that is given in IS 10262 2019. And workability criteria, one has to understand. So what is the slump you are aiming at as per IS 456 class 7? You can see that particularly we go for the 0 slump, but to differentiate, we just measure the compaction factor test for 0 slump. So usually the 0.75 to 0.8 compaction factor you achieve for the the pavement, concrete or whatever. This is a very low degree of workability. And for mass concrete and canal linings and other beams, walls or lightly reinforced sections, we go for the low degree of workability, wherein the slump is between 25 to 75. And heavily reinforced sections, medium workability, that is between 50 to 100, and pumped concrete is medium again, between 75 to 100, and trench fill, in situ piling works and all, high workability you require is between 100 to 150, and cremi-concrete, you just pour the concrete there, wherein very high workability, wherein 150 to 200. We're talking about the horizontal slump, but nowadays people are talking about self-compacting concrete. Vertical slump, what we are talking about. And nowadays people are talking about self-compacting concrete, wherein they measure the horizontal slump that varies between 500 to 800 mm in spread. So most of the placing conditions, we use the internal vibrators and the needle vibrators, and for the tremi and in situ piling, vibration is not required because already the slump is 100 to 150, and with a gravity it will get filled. Many times you have seen in the video, mixing time, the minimum 2 minutes. The mixing time shall be at least minimum 2 minutes. You make sure the concrete is consistent. The mix is consistent. All the mix constituents are properly mixed. You have to make sure. And workability has to be checked at frequent intervals. So this is very important. And also the placing of the materials also makes a point, particularly when you're going for, or when you're making the fiber reinforced concrete. So you have to place the coarse aggregate of 50%, and then you put 20% of your fibers, then 50% of sand, again 20% of fibers. So there is a way of mixing also. Then you have to put, rotate, and then put, rotate. So that's why, particularly fiber reinforced concrete, if you need the fibers to be spread uniformly, the mixing sequence should be different. So you can see the difference between the fully compacted to vibration or hand compaction to insufficiently compacted concrete. When the water cement ratio increases, the strength reduces, right? Suppose if you same, but even though if the water cement ratio, if you keep it constant, And if you're not compacting properly, okay, so when the water cement ratio reduces, you have to compact more. Very important. But the traditional methods, earlier I have mentioned, in traditional mixed design, this is what we're talking about. There are limitations in traditional methods. So the workability, we talk about water paste content, not by superplasticizer or whatever. And they don't consider in traditional mixed design the mineral admixtures and unconventional cements, particularly PPC, PSC, and grading curves. They don't consider grading curves, aggregate grading curves in traditional methods. So these are some of the limitations. That is why you have to go for the method of mixed design. So let me take an example with fly ash as admixture as per IS 10262. So the details are grade is M40 we are designing and type of cement 43. Mineral admixture we are using fly ash as per IS 3812. Maximum aggregate size we are considering 20 mm. Minimum cement content is 320. Maximum water cement ratio 0.5. Workability requirement is 120 mm slump. Exposure condition is severe. That is why we limit the maximum water cement ratio as 0.45. Severe. That is why we limit the minimum cement content as 320. So entire mixed design comes from the exposure condition. The base is exposure condition. Based on that, we go further in designing the mix. And we are designing the M40. However, the minimum grade of concrete is M30, but here in this case, we are designing M40. So they want to pump the concrete and the degree of supervision is good. They're using crushed angular aggregates, and anyway, maximum cement content is limit for any case 450 kg per cubic meter. And superplasticizer, we are using it for this particular mix. Okay, this is the mix details given. So test data, the cement content properties are given as the typical specific gravity of the typical specific gravity of cement is 3.15, and fly ash is around 2.2. This data is given. Chemical admixture, superplasticizer is conforming to IS 9103. Specific gravity of the materials are given 2.74 and 2.65. Water absorption, they've given as 0.5%. In case of coarse aggregate, fine aggregate, it is 1%. So they wanted to blend the aggregates 20 and 12.5 because it has to satisfy the graded aggregate requirement. So actual data, it is present over here. If you mix 50-50 ratio, it is conforming to graded requirements. And the fine aggregate is conforming to zone 2. The data is given. Okay. So we have to go, the first thing is we have to find out the target strength. Target strength formula, F-CK is equal to characteristic strength plus 1.65 times the standard deviation. X factor, or otherwise you can take the X factor based on the grade of concrete. This is what it is given in IS 10262 2019. Standard deviation, you can consider 3.5 for standard M10 and M15. But RCC, the minimum grade of concrete, we go for M20. So the standard concrete M20, 25, go for 4 is a standard deviation. And for M30 to 60, you're going for 5 as the standard deviation, and 65 and above, up to 80. 6 is the standard deviation. And or otherwise, you can add the X value. So either 5.5 or 6.5 or 8, we can take it as a, the additional strength. So if it is a M40 grade of concrete, 40 plus, 6.5 in case of X we are paying, or otherwise 40 plus 1.65 times the phi. Okay. That's what I have given here. So FCK plus 1.65 times the standard deviation. Our standard deviation here is M40 grade of concrete, it is phi. So 40 plus 1.65 times the phi, that is 48.25 is your target strength. So you got the strength, target strength as 48.25. You have designed the concrete. You have to design the concrete for 48.25 MPa. So the new IS 10262 2019 goes back to the standard curves between the water cement ratio to compressive strength. Earlier, before 2009, we are using the same curves. So the improved curves are given here. That is water cement ratio to compressive strength curves. So for 48.3 MPa, if you can see, for OPC 43 grade. So they have given for 33, 43 and 53. Here in our case, it is 43. So 48.3, if you go straight and find out. So this is the second line, okay. 48.3, when you go here, it comes around 0.36 for OPC 43. So 0.36 is good enough. You can adopt because it is less than 0.45 as the maximum water cement ratio limit for exposure condition we have seen here as 0.45 because it is a severe condition. So 0.45 is the limit. 0.36 is not at all a problem. We have taken it from the curve based on the strength what we obtained from the target mean strength, which we have done here, right? So the same thing. You can see here, M40, sorry, exposure condition we have to look into it. Severe condition, the exposure condition is 0.4. So this is where the people get confused, right? So we are designing M40. Don't think M40, the maximum water cement ratio is 0.4. No, it is based on the exposure condition. Severe, but the minimum grade is M30, but we are designing M40 grade for severe condition. That's why the maximum free water cement ratio is 0.45. Let us see what are the various type of exposure conditions. Mild, moderate, severe, very severe, and extreme. These are the 5 exposure conditions. As I mentioned, the concrete surfaces contact or buried under aggressive soil comes under moderate condition. That's why footings we design based on the moderate condition, exposure condition. Severe, concrete completely immersed in seawater or exposed to coastal environment. Coastal environment generally comes under severe condition. You can see other different type of exposure conditions. Accordingly, you have to take these exposure conditions and accordingly you have to limit the maximum water cement ratio. So let us go back to our case. So next is selection of water content. So selection is based on the table 2 of IS 10262. There are 3 types of aggregates we use for normal concreting: 20 mm, 10 mm, and 40. 40 generally we go for the road works or otherwise some of the other special ones. Typically we go for 20 mm down aggregates. For 20 mm down aggregates, the maximum water content we have to take is 186 liters. So 20 mm, so we have considered 186 liters. So this 186 liters is for the slump of between 25 to 50 mm. Please remember, this particular table is for 25 to 50 mm slump. 20 mm down aggregates, 186 liters. That too saturated Ssd condition, right? But in our case, data if you see, sorry I'm going back. Our case, the slump what we have to take is 120 mm slump. So for 120 mm slump, what we have to do, you can see the corrections that are given here. For every slump increase of 25 mm, you have to add 3% of correction you have to do in water. So 186 liter is your water. 25 mm, suppose ours is 125 mm. So up to 50, 186. 75, 3%. 100, 6%. 125, 9%. So 9% of additional water correction we have to take. But ours is 120 mm slump. We have done the iteration. Okay. So 186 plus 8.4% it has come into 186 by 100. So 201 liters of water is for the additional slump. So there are other conditions, because if it is a crushed angular, no need to take any correction. If it is a rounded gravel, then you have to reduce the water to 25 kg. Suppose if you are using water reducing admixture, you can reduce up to 5 to 10% of water. It depends on the admixture time. So the water is 200 liters for 120 mm slump. As we are using the superplasticizer, it can be reduced up to 23%. Okay, because the based on the trials of the superplasticizer, so it was found that water reduction can be achieved 23%. So 23%, 100 minus 23% is 0.77%. So 77% of 201 liters is 155 liters of water you can add, because we are using the superplasticizer. So how to know how to find out the superplasticizer dosage? The very important or very famous test we have, that is called Marsh cone test. It's an inverted cone with aperture 8 mm, wherein you find the optimum dosage of superplasticizer. This is the typical Marsh cone. Here what we do, we find the flow time, viscosity of the fluid. We'll fill it, the paste, and then we measure the time taken for 500 ml of paste to flow out of the bottom aperture. Then we measure the superplasticizer versus the varying superplasticizer dosages. We measure the flow time. Then we find the superplasticizer dosage to flow time. After, if you keep on adding, say, 0.2%, 0.3, 0.4, 0.5. At certain point, you can see here, after this point, so the flow time is not increasing. This is the optimum dosage. This is what we call it as a saturation point. People say, it exhibits at around 140 plus or minus 10 degrees. Based on the extensive experimental study, people say exactly at that point you get the optimum dosage of superplasticizer. So these are typical trials we have done. So for 0.1% of superplasticizer, we got 17 seconds. 0.2 it is 15 seconds. 0.3 it is 11 seconds. And after 0.3, even if you use 0.4 or 0.5, it is unchanged. So it is showing 11.7 only. That means the saturation of superplasticizer is achieved. So this is how you find out the optimum dosage of a chemical admixture or superplasticizer based on the Marsh cone test. Okay, let us get back to the calculation part. So we have found the water cement ratio is 0.36. We've got, and then based on the water cement ratio of 0.36 and then water content 155 liters, we just found. So we can measure the cement content, right? So water to cement is is equal to 0.36, and your cement you can find out by water cement ratio. So 155 by 0.36, we get around 431 kg per cubic meter. So once you get this cement content, you have to do two checks. One is whether minimum and maximum cement content requirement is satisfied. For severe condition, the minimum cement content condition is 320, right? And maximum is 450. It should not be more than 450. So it is more than 320 and less than 450. So your cement content is fine. But as per durability criteria, you have to do adjustments for minimum cement content. What does that mean? For 10 mm, suppose if you are taking the 10 mm coarse aggregates, so in place of 20 mm, you are going for 10 mm down, you have to additionally add 40 kg per cubic meter. What does that mean? Your minimum cement content requirement is not 320, it is 360 kg per cubic meter is your requirement. If you are using maximum size of aggregate as 10 mm. Okay, I just wanted to give you a hint here. Next is fly ash. Based on project, you can decide the percentage of fly ash. Sometimes based on experience and trial, you can increase even cementitious materials. So here we have increased the cementitious material content is 10%. 431, 10%, because we are adding the fly ash. 431, 10% is 474. So water content is 155. Again, you back calculate, that is 155 by 474.327. So we can take fly ash at 30% of cementitious material. Out of 474, 30% is 142 kgs. And reduce that 142 kgs in your 474 is 322 kg per cubic meter. So fly ash is 142 and your cement is 322. So we got cement, water and fly ash. Now we have to find the coarse and fine aggregate ratios or the quantities. There is one more table between the water cement ratio to volume of coarse aggregate. It is very easy to remember. If it is a zone 1 20 mm aggregates, 0.6, and when the zone increases, zone 2, zone 3, zone 4, your 0.6 will become 0.62, 646 with a 0.02 variation. Similarly, for 10 mm down, 0.44 it starts and it reduces to 464850. Increases your coarse aggregate. So when the zone of the fine aggregate is finer, your coarse aggregate content will be more, because zone 4 of fine aggregate is more finer in nature. Generally, we don't go for concreting zone 4. We generally use zone 1, zone 2, zone 3 fine aggregate sand, okay, for the concreting purposes. So here in our case, our coarse aggregate is 20 mm down, and then zone 2 is our fine aggregate. So zone 2, 20 mm, 0.62 we have to take. The present water cement ratio is 0.327. But this table, whatever I am mentioning, is for water cement ratio of 0.5. If you are reducing the water cement ratio, you have to increase the coarse aggregate content by 0.01. So 0.327, it is 0.62 plus 0.01. Every 0.05 change we have to reduce 0.01 if water cement ratio is increasing. But in our case, it is reducing to 0.327, 0.5 to 0.327. So 0.5 to 0.45, 1.01. Again 0.4, one more 0.01. So 0.01, 0.01, 0.02, and one more 0.35. This is 0.0346 you get. So the corrected volume of coarse aggregate is around 0.64 you will get. But ours is a pumpable mix. Again, there is one more clause for correcting coarse aggregate. For pumpable mix, you have to reduce the coarse aggregate to 10%. So 0.64 will become 0.59 because you're reducing 10%. Because when you're pumping, too many aggregates should not do that because it gets blocked. So that is why for pumpable concrete, they reduce coarse aggregate to 10%. So once you get the coarse aggregate content is 0.59. So 1 minus 0.59 is the remaining is your fine aggregate, that is 0.41. So take the total concrete as 1 cubic meter and mass by specific gravity into 1 by 1000. You get your volume of cement, that is 0.15. Here in this case 332 kgs by 3.15, what we found. Similarly, fly ash volume also we find. Water volume also. And chemical admixture volume also you can find out. The volume of all in aggregate is cement minus 1 minus cement minus water minus fly ash. This is around 0.66 cubic meter of volume is there as an aggregate. And entrapped air is 0.01 cubic meter we consider. So generally for 20 mm aggregates, we consider entrapped air as 1%. So that is why we can take it as 0.99. That's why here only we have deducted 1 minus 0.901. So we have to find out the mass of coarse aggregate. This is 0.6615 into what is the coarse aggregate? What we found, 0.59. So 0.66 into 0.59 into specific gravity of the coarse aggregate into 1000. So you get the required amount of mass. Similarly, for the fine aggregate, you get the 0.6615 into 0.41 into specific gravity into 1000. What you get is your mass of fine aggregate. So this is how you get the both fine aggregate, coarse aggregate, cement, fly ash and water and the water cement ratio. So this is the trial number 1. So with the trial number 1, you have to find out how much slump you are getting. Are you getting compressive strength? You have to check, and then if you are not achieving, you have to go for the trial 2. Generally what we used to do, trial 1 we do it and then we go for the accelerated curing test for the next day. If we are not getting the required strength based on the accelerated curing method, we immediately go for trial 2. We will not wait up to 28 days. So accelerated curing method is one of the important methods wherein without delaying the anyway, we test after 28 days only we'll give the report. But quickly we do number of trials such that the time will not get wasted. So this is for high strength concretes. So this is what I spoke about, how to design the normal concrete. When it comes to the high strength concrete, you can see the volume of coarse aggregate to different zones of concrete. For high strength concrete, they don't use zone 4. You can see here. And zone 1, if it is 20 mm, it is 0.64 you are using, and zone 2, it is 0.66, and so on. And recommended water cement ratio, water to cementitious materials for high range water reducing admixtures. You can see here how much water to cementitious materials you can 100 MPa strength. If it is a 20 mm down, you can go for 0.24 with high range water reducing admixture. These are some of the guidelines they have given. In mixed design, always guidelines. It is not as you have to exactly follow. These are the guidelines given. As long as you achieve your workability, achieve your strength, you can follow. This is the water content per cubic meter of concrete for high strength concretes. 20 it is same, 186 liters. 12.5 it is 195. 10 is 200 kilos. This is given in the new code. Even the entrap date. For 20 it is 1% earlier. It is only 0.5%. 12.5 it is 0.8 and 10 it is 1% it is allowed. Yeah, this is a very, very important and very interesting table that is given in IS 10262 new code. How much dosage of mineral admixtures we can use in particularly concrete, high strength mixes? Fly ash, one can go up to 15 to 30% is the maximum limit. GGBS, one can go up to 25 to 50. I'm talking about high strength mixes. Normal mixes, you can go up to 60, 70. Metacavalin or silica fume, we go in a very small quantities, that is between 5 to 15%. The recommended doses of mineral admixtures, you can see here. Having seen this, you need to understand volume fractions of mixed proportions. As you've seen in the normal concrete, the volume of coarse aggregate, you can see here. How much is the volume? You can see 0.6615. 0.6615 into, if you take 0.6615 into your 0.59. So 39% of your coarse aggregate and 0.27% of your fine aggregate is present in your normal concrete. And your paste is around 27%. And paste is nothing but water and then cement. Let us see what kind of proportions or the volume fractions we find in high flowing concrete, particularly self-compacting concrete. Let us see. So these are the typical mixes you can see collected from various parts of the world. UK, America, Canada, France, Spain, Belgium, Singapore. The type of filler they've used is varied from fly ash to limestone to GGBS. The powder content or the cementitious material content, you can see it ranges from 450, 470 to almost up to 700 kg per cubic meter when you combine both cement and filler. So when you calculate the volume fractions, it is very important to understand the volume fraction of mixes. When you observe all these mixes, the volume of fine aggregate and volume of coarse aggregate, it is more or less equal. Or sometimes your fine aggregate is more than the coarse aggregate. You can see here, right? You can see either it is equal or fine aggregate is more than the coarse aggregate when you see the volume fractions. But in normal cases, volume of coarse aggregate is more when compared with the volume of fine aggregate for normal concretes, because it has to flow. It has to take the coarse aggregate from one point to another point, that too in a suspension state. So you have to maintain the motor, the fluidity, the flowing behavior by keeping the coarse aggregate into suspension. So self-compacting concrete, typically the volume of fine aggregate is equal or more than the coarse aggregate. Point number one. When you are looking into the volume of paste is nothing but cement plus cementitious material, either fly ash or GBS, plus water. This volume of paste, when you look into the normal concrete, it is around 23 to 27%. But in case of self-compacting concrete, wherein you need a large amounts of paste. But in all other parts of the world, I'll talk about the Indian condition also. The volume of paste ranges from 0.35, 35% to 41% when you take the total volume. So 35 to 41%, mean is around 38% of volume paste is there in the self-compacting concrete. In normal concretes, it is only 25, 26%. When we look into the Indian researcher mixes of self-compacting concrete prepared by different people, initially a lot of work is being done at L&T, Mr. Subramanian, and some of the people they work, Amit Mittal, Praveen Kumar, and a lot of people they worked initially. Even myself also worked on this particular self-compacting concrete way back in 2002 and 2003 at that time. Where in Indian researchers, you can see the volume of paste ranges from 0.37 to 0.46, because here the mean itself is 0.38, but here the volume of paste is more than the other countries. Why? Because of not having a proper, aggregates. We have it. And any small change, because of the shape of the aggregates, what we get, we need a more paste to get the required flow parameters. So other parts, when you see these mixes, SCC mixes, the mean value is 0.38 and 40% paste volume is required. 60% is your aggregate volume. Volume fraction of fine aggregate is equal or more than the coarse aggregate. But Indian researchers, it is 0.4 to 0.46. But paste volume is higher because of the angular crust aggregates, or sometimes we avoid using the VMA. So viscous modifying admixture, instead of not using viscous, you can go for the more paste content. So these are the typical properties one has to do. QA/QC test before doing the mix design. Even the water and admixture, these are the various codes: 3025 for water, 8142, 1199, 6925. These are the IS codes which we follow to measure the various properties of the different constituents. Okay, nowadays it is very important to go for this special test. Many people are making it mandatory for these special structures. So now it is becoming common to go for water permeability test. People are asking about initial surface absorption test. People are talking about RCPT test. They are asking the results. Going for subctivity, water absorption test. I just wanted to give you a glimpse. This is the depth of water penetration test, IS 516. This is water permeability test. This is how you carry out the test. You apply the required pressure, water pressure, on the surface of the concrete, and then after the end of the program, you split the cylinder into two and find out the depth of penetration. Another one is the initial surface absorption test. This is the time taken for the water to move by a certain distance after closing the tap. So they find this initial surface absorption, how much absorption. This is an RCPT test. How many coulombs of chloride it passes through. The requirements you can see here. If it is more than 4,000 coulombs it passes, the chloride permeability is high. If it is between only 2,000 to 4,000, it's moderate, and 1,000 to 2,000 low, and less than 100 it is negligible. Some of the trials done at Saturn laboratory, you can see here. These are the mixes, M40 mix with cement and GBS, and these are the weight proportions. This is the consistent what they got for M40, the 49.4. This is another mix M30 grade of concrete with the required weight proportions and 41. The target means 28 days what they've achieved. They've used the dosage of admixture 375. So these are some of the other mixes they carried out. This is how they give the test report for typical quantities. Yeah, this is a very interesting durability test. They've asked for this Amravati site, that construction in Vijayawada, wherein the water penetration test, they've carried out RCPT, 17-13 coulombs, and initial surface absorption and water absorption. Why these are important? Because for structural safety of tall concrete buildings, the criteria they have mentioned in IS 16700, you can see here some of the specifications, wherein how much strength they require, and what is the rapid chloride and RCPT values. For foundations, it should not be more than 1000. For superstructure, it should not be more than 1500 coulombs. Water penetration, the maximum depth should be 15 mm. So in code itself, they are giving the criteria. Okay. And coming to some of the tests which are related to the. Yeah, 1 second. Yeah, these are some of the non-destructive tests, very important, particularly the rebound hammer and ultrasonic pulse velocity test. I just wanted to give you a glimpse because the concrete, once you prepare and once you put it inside, we have to handle properly. If you don't handle properly, you just have to, because the client will ask what is the strength after placing it? We have a doubt. So then you have to go for the various other non-destructive tests. So this is an ultrasonic pulse velocity test wherein you send the pulse and measure the concrete quality. So how much is the pulse velocity? If it is above 4.5, it is excellent. And if it is 3.5 to 4.5, it is good. Below 3 means the velocity, if it is less, then it is doubtful. Even if you are not satisfied with both the tests, either rebound hammer and pulse velocity, one will go for core cutting and then check the strength of the concrete. So you cut the core and then you find what is the failure and how much is the strength. This is a typical core. So for a durable concrete to achieve the mixed design, if you are doing, you have to follow 7 C's. One is the designer should make sure you should provide a sufficient cover. You have to reduce or avoid congestion such that the concrete is properly placed, and you should have a sufficient amount of calcium hydroxide to form the CSH gel. And you have to place sufficient numbers of cover blocks such that you maintain that cover. And you have to make a lot of checks before concreting. And you have to properly compact, and also you have to properly cure the concrete. I'm coming to the summary of my presentation. The mixed design should fulfill durability requirements. Mainly exposure condition is very important. And you need to ensure compatibility between various ingredients, particularly chemical admixture and cement. Very, very important. Many times the compatibility between the admixture and the cement is a main problem, whether to have the bleeding or whether to have the segregation. So you should have a proper compatibility between the cement and admixture. And the carbonation chlorides are a major concern, particularly Indian conditions. So you have to go for a durability test, particularly when you're going for important structures, particularly in the coastal environment. So durability tests are mandatory. And use of supplementary cementitious materials like fly ash or GGBS are recommended. It has to be encouraged to achieve the denser concrete. People having a doubt on, if you add fly ash, so you have to properly add how much to add, and you need to know the behavior of the fly ash when compared with the GGBS when you are adding. So long-term strength or early strength, you need to understand. And as per standards, one has to go for maintaining proper cover and cover block just to be checked before concrete. So with that, thank you, and the floor is open for questions.
Participants, if you have any queries, you can ask sir during this question answer session.
Maybe
sir, we have a few questions.
I will just read out. I've seen in the message box.
Okay, sir.
An increase in the sand to cement ratio from 0.8 to 1 in a cement mortar mixture would result in lower density and compressive and flexure strength. Increase in the sand to cement ratio from 0.8 to 1. I think Fakir Muhammad has asked the question. I don't know where he is referring. Maybe my initial slide, or let me check. My initial slides. I don't know where he is referring, but let me go back to the question. Increase in the sand to cement ratio from 0.8 to 0.1 in cement mortar could result in lower density and compressive. Yeah, when you increase the sand by keeping the water constant, I don't understand your question, because again the water is also makes a point. Okay, 1 second. Yeah, just give me a second. So it depends on how much water you are putting it in the mortar, and that depends. If it is a same water, definitely sand to cement ratio. Again, it also depends on which cement and things like that. Next is the percentage variation between direct and indirect test of ultrasonic pulse velocity test. What is percentage variation between direct and indirect test? There is a lot of literature that is available, but indirect test will give you 50% less value. When you go for the direct test, approximately. So if I add steel fibers in concrete, how much percentage of compressive strength increase? So steel fibers we generally add to increase the toughness and also to increase the flexural behavior of the concrete. But compressive strength incidentally increased by 5 to 10% only. 5 to 10%, it depends. Anybody else? You can unmute and ask if you want to ask questions related to the next design.
Any more questions from the participants? So there is a request from the side of the participants to share your PPT, sir.
Yeah, maybe I'll just make it a PDF and then I'll send it. Okay, later. Yeah, sure.
Thank you, sir. Any more questions?
Definitely, I'll make a PDF and I'll send the presentation.
Someone has raised hands. Who's that?
You can ask a question, no problem.
You can switch on your mics and speak. If you have any doubts or queries. Anyone? So, sir, shall we wind up the session, sir?
Yeah, no problem. No problem. Okay.
Any more question, participants? The feedback links will be shared with you now. Just fill it up within 15 minutes. It will be open only for 15 minutes. Now, let me move on to the vote of thanks, which is entrusted with me. Respected Dr. Jagdish Vengla, sir, Dr. Jacob Chandapalli, sir, our HOD, faculty members, and our most valued invited guests. No duty is more urgent than returning thanks. It's my privilege that I have been asked to propose a vote of thanks to all those who have helped us in making this program a success. I would like to thank our distinguished speaker, Dr. Jagdish, sir, for enlightening us with his knowledge. The session was full of knowledge and interesting new things. It gave us deep insight into the topic and clarified many mysteries regarding concrete mix design. The points that Sir told us about the design details and even the minute things we must consider during the same were really informative, sir. Thank you once again on my behalf and on behalf of my institution for being here with us this afternoon. I'm pretty sure that the precious knowledge he imparted will definitely help us in future. Once again, thank you, sir. I would like to express my profound gratitude towards the management and our beloved principal in their absence, giving us an opportunity to organize this lecture. I would like to thank our beloved HOD, Dr. Jacob Chandapalli sir, for his moral support and guidance throughout. I'm happy to register my sincere gratitude towards our faculty and staff members for their enormous cooperation in the successful organization of this event. Finally, a big thanks to the wonderful participants from all over the country who have turned up in great numbers for paying attention and learning. Thank you for making this program a big success. With this, I end my speech. Once again, thank you for being with us this afternoon, and it has been a great pleasure to be with all of you. Thank you very much. So I have shared the feedback link. Kindly fill it up within 15 minutes. It will be open only for 15 minutes.
So thank you organizers and thank you all the participants. I'll send the PDF of my presentation to organizers. You can collect it from organizers. So I'm signing out. Thank you once again.
Thank you, sir. Participants, kindly fill the feedback form. It will be only available for 15 minutes.